All right, the next thing I want to talk about is a super powerful feature of 5G NR and other types of cellular systems, which is CSI feedback, or channel state information feedback, and that can dramatically improve the link adaptation. I'm going to show you basically how it works, and just with some very simple algorithms can provide a lot of information back to the transmitter. So let's go through this. So we saw that trial and error type rate adaptation is going to be inexact and will generally result in a lot of wasted attempts. So almost all cellular systems use some kind of channel quality indicator, or sometimes called channel state information feedback back from the receiver. In most cellular systems, these consist of CSI or CQI reports, maybe in the order of about 100 times a second, and that will basically tell the base station, which is trying to make the scheduling decisions, what is that channel quality, and then it can make a much better MCS selection on the downlink. So let's take a look at how that works. So in the NR standard, they introduced a signal called a channel state information reference signals. That's a mouthful, but basically it's by a simple idea. So imagine that you have your base station, or G node B, and your UE, and there's some downlink fading channel. The G node B will periodically be sending these signals to the UE. That is, like everything in NR, completely configurable, but let's say on the order of 5 to 10, once per 5 to 10 milliseconds. The UE can then measure that channel quality from that reference signal, and then it can go ahead and send that quality or CSI report saying, hey, my SNR is X. Based on that SNR, the base station can then select the MCS whenever it decides to schedule the UE and make that assignment with a much more accurate selection. So that's the basic principle. It's pretty simple. Let's go into a little bit more detail. The first thing is about the configuration of the CSI RS. So again, as I said, it's very configurable, and it's no need to go into all the details. I just want to say a couple of things. First of all, there are two types of reference signals. The first are what are called zero power signals, which you can measure noise, and non-zero power signals where there's actual signal, where you can measure this actual signal strength. If you take the ratio, of course, you get the SNR. Where exactly they go, though, is super configurable. The NR standard allows you to do virtually everything. But what is great is that the 5G toolbox in MATLAB can do all of this configuration for you. You just give it a set of parameters. I've shown them here. Again, they're all in the demo. There's no need for you. I'm certainly not going to spend the time this unit going over all these details. Again, the 5G toolbox also comes with lecture videos, and you can get all the details. But you can see some of the configuration parameters, like its periodicity, its density, where exactly it's located, and so on. And basically somehow trade off this estimation accuracy and the overhead. Just to give you an illustration of what one of these configurations looks like, I just created a very simple version. First here, I put in a zero power CSI reference signal, so the base station is actually transmitting nothing here. So that will allow the UE to measure the noise. And then you can also, on this yellow part here, you can actually transmit the signal. This on the left is what is the allocation in one resource block, and then that is repeated like this. All right. This is actually not a very sensible configuration, because as I'm going to show you, you actually don't need this zero power, but it'll just make the math very easy for us initially. In this case here, it looks like it's occupying a lot, but typically in the way it would be just configured here is that it's only being sent once every 10 milliseconds. So if you look at this, I'm allocating 6 of these resource elements out of 14 times 12 in this block, and then only doing that once every 10 seconds. So you're under 1/3%, so it's not a problem at all in terms of allocation for this. All right, how do you use this? Well, it's pretty straightforward. Here's a very simple idea, and I'll get you an even better algorithm in a second, but this is super easy to understand. All right, so on the zero power CSI RS, you're only getting noise. So I could make a noise estimate just simply by averaging all the resource complex values I see. So just take, if there's n of them, just take n and take the average. Super easy, and that will give you a noise estimate. Then on the non-zero power CSI RS, well, I have the actual signal here, and I plus the noise. So if I take the average value of this, of course, I'm just going to get the signal plus the noise. So then if I could take that average value here, I could estimate the SNR, if you like, on each symbol by taking that expected the value squared, subtracting out the noise, and then dividing by the noise, and that will give you the SNR on that symbol. All right. Just as an example simulation, which again is all in the demo, I have created a simple 3-path channel, and this shows you the channel, the time varying frequency response over one resource, one slot. So in this case, there's not much not much time variation over this slot because the Doppler spread is not that large, but you do see some frequency variation, as you can see here. All right, so again, check it out in the demo, and you can look through that. Now, when you do this, at each point, I just gave you that very simple algorithm to estimate the SNR. You basically took all the zero power and you measured the noise, and then you just measured the signal strength on each of these powers, and you get these orange squares, orange circles for the SNR. And then you can see, of course, on an individual element, this is pretty noisy. It roughly tracks the SNR of the true channel, but it's pretty noisy. So, of course, what you would do in response is you would try to take some average value of that when you report it. So you could do what's called a wideband SNR, which you would take the just average across this whole band. Now, before we go on more, you can also just do that whole estimation without the zero power CSI RS. You could just do it on the non-zero power. And this is, again, pretty simple. The idea is this. Imagine that I can group those CSI reference signal resources in groups of small groups, let's say within a resource block. And maybe let's say there are K of them. So each of these, I would have the following. I'd have my receive signal is H times a known signal X and WK. But so it's important here that there's no index K, because I'm going to assume that over the group I'm going to average, that channel is constant over this period. That's the case if this assumption is valid, and that depends, of course, on the coherence bandwidth of the channel, then I can just find an estimate for this H just by doing a simple linear estimate, because I know the X's on the reference signals, and I know the R's, so I can estimate H with standard linear estimation, and then from that H hat, I can then subtract that out to get the estimate for the noise, and then I can get that estimate for the SNR on that group. And then I could go ahead and average that SNR, if you like, over multiple groups, depending on the frequency resolution of the report back that is needed to the base station. I've put a simple implementation in MATLAB. It's not whatever 8 lines of code. In this case, I've averaged over 3 resource elements in each block, because there are 3 resource elements per resource block. I go ahead and I just do some reshaping of that of the estimates to just do the averaging, which is done here. And then I average the noise, and then I can average the signal and then return back that estimate. So it's really basically very, very simple to do a quick CSI estimate in MATLAB, and this will actually get you pretty good results. Now, that is estimation on the downlink. The CSI estimation, the uplink's a little different, and a lot of students and people just entering this get confused. So the reason why people get confused is the uplink is power controlled. So it's not like the case that the base state, the UEs transmit at a fixed power. Instead, what happens typically in most cellular systems is that there is a reference signal that the UE sends. And that could be that physical uplink control channel that we're talking about, or there's other reference signals like the sounding reference signal. I'm not going to get into them right now. But the base station tries to maintain these at a fixed SNR. So what it does is it measures the SNR on these signals, and then it feeds back with some power control commands to a UE, so it adjusts its power. If it's coming in too weak, it tells it to increase its power. If it's coming in too strong, it tells it to decrease its power. And the reason it wants to do this because it wants the UE not to waste any battery that it doesn't have to keep it at that target level, and it also doesn't want it to create any additional interference into other base stations unnecessarily. But as a result of this, you can't use the reference signal power itself as a measure of the channel quality because it's always being targeted at a fixed SNR. So the question is what to do, and this is where lots of students get confused. You need one other piece of information, and that is typically what is done and called a power amplifier headroom. The idea is basically very simple. So imagine that the UE is sending a reference signal at some transmit power. And then because of power control, it comes in at some SNR. And the base station can control it to this SNR, or it can measure it in any case. Now, additionally, what the UE says is, in addition to this reference signal, it tells the base station, okay, I've controlled my reference signal, as you've said, but I have delta dB additional headroom I could transmit. So, for example, if that reference signal was taking the UE 0 dB and the maximum power of that UE was 23 dBm, then the UE could say, hey, I have 23 more dB of so-called headroom. Now, based on this, the base station could say, oh, I get it. So you're coming in here, but if you transmitted at your maximum power, you would come in at delta. I know the SNR that you're currently, of your reference signal is coming in, so if I add delta to that, I could compute the theoretical maximum SNR that the UE would come in if it transmitted all of its power. And that it can use as the basis for scheduling. Now, it might not choose to do this for other reasons. For example, it may not want to waste the battery of the UE. It also might learn that if the UE does transmit at that maximum power, it could cause a lot of interference into neighboring cells. We're not going to get into that in this class. That's another whole super interesting area of multi-user scheduling in the uplink. But that is the basic way it can learn about the channel quality. So it doesn't learn it just from the reference signal itself. It also needs some information here which tells it how much additional headroom it has. All right, couple more points. One thing is that the channel state information, even if you implement it well, will have some errors in it. For one thing, of course, a receiver doesn't measure the CSI accurately exactly because it's some noisy measurement on these reference signals. So in the demo, I kind of give a little plot of this, and you can see the estimates, and they're pretty close to what is the actual CSI or the wideband or average SNR at these times, but they're off a little bit. That in this particular case is not so much, but what's a bigger error is that there's going to be a time delay between the CSI measurement and the actual time it gets used. Because there's a delay in sending that report to the base station. And then the base station takes some time to process that report, and then it makes a scheduling decision, and the data goes out after some time. And so, for example, here, if I sent this report, I might actually go ahead and make a scheduling decision later, and you can see it's several dB lower, or even significantly lower in this case down here. All right. So that's just something to keep in mind, and that will trade off. You will get this part lower if you have lower overhead, and you will also get this part lower if you have a faster response. All right, the whole topic of CSI is super interesting. The 5G NR standard, for one thing, has enormous numbers of features for configuring these and trading off these different variables. It's also not just the configuration of the reference signals, but the actual reporting itself. There's actually what is called wideband reporting, where you report a single average SNR. You can also report SNR per subbands. And when we talk about spatial multiplexing, you report them on different layers. And how to optimally use this is somewhat complicated because there's just so many knobs that you can tune. Unfortunately, we won't have a chance to get into all of these in this class, but maybe this will give you a little idea of some of the key trade-offs. So with that in mind, I'm going to have you, as a little exercise, just implement a very simple CSI tracking of this narrowband fading channel, and you should get a plot like this, which I showed you earlier, which shows this channel varying over time and then your estimates at different points. So if you get this done, you've actually built a little CSI reference signal tracking system, and then you can go on to our final section on hybrid ARQ.